All right, so we want to do this Hess's law problem. We have this hydrazine, this hydrogen peroxide making nitrogen and water. Odd reaction, but okay. What are we going to do with this first equation? Leave it? Why do we want to leave it as is? I have water in the liquid state on the product side, and
the N2H4 in the liquid state.
I've got my hydrazine here in the liquid state. So we want both of those things in those positions, so we're just going to leave that. It looks like we're probably going to have to do some extra water molecules somewhere in here, but I see more water down here, so we should be okay. So anything else in this we like?
The N2.
The N2 in the gaseous phase on the product side is also something we need. So the only thing that's up here that we don't want is somehow we need to cancel out this oxygen. There are no oxygens on the product side to cancel that out with, so we're going to need to do that. So what do we want to do with this?
Flip the fourth equation.
Flip the fourth equation. If I flip the fourth equation, I'll get H2 gas and O2 gas. So all of this is gone because it's on the other side. What else do I do?
Multiply by 2.
Can I use something else before that? I just flipped the equation. Before I forget, what should I do?
Change it to a positive.
Yeah, I need to change this sign over here, otherwise you'll forget. And then, what did you say?
Multiply by 2.
Multiply this by 2? Okay, if we multiply this by 2, then I've got my hydrogen peroxide as a reactant. I have to multiply that by 2, and then the oxygen by 2, and then this value here for the enthalpy by 2. Okay. Now what do I got going on?
You have half an oxygen in here.
I have half of an oxygen here. I've got a full oxygen here. I need this to be gone. I need this to be gone. That, and that to be gone. So how do I make these guys disappear?
You multiply that equation.
If I multiply this equation by 2, then I can cancel out these 2 hydrogens with those 2 hydrogens, since this is a reactant and that's a product. What else can I do?
Cancel all the oxygen.
So there's 1 oxygen, 2 oxygens, cancel out with those 2 oxygens. So that looks good. And then I have these other 2 water molecules in the liquid state. So these 2 together add up to that 4 for that one. All right, so these equations are set up correctly. I've got just the stuff that I want left. Everything else is canceled out. So then those numbers just need to be added up. So I've got a negative 622.3 plus negative 285.8 times 2 plus 187.8 times 2. I get negative 818.3 kilojoules per mole. So what kind of reaction is this? Endothermic or exothermic? Yeah, the negative sign means that the reactants gave energy away. And so in this case, putting these guys together would produce a whole bunch of heat. Okay.
Why does the 2H2O2 gas change to a liquid at the bottom?
2H2O, where? I don't see it.
On the bottom equation, it's a liquid.
That's a typo. Here to there. That's a typo on my part. This right here is supposed to be a liquid. Thanks. I need to change that. Typing that. Don't have a piece of paper, so. Typo. This is homework 3, right? Yeah. H2O2 gas. Needs to be a liquid. Okay. Thanks, Lexi. All right, so now we want to calculate the energy needed to heat a 250 gram chunk of copper from 22 degrees Celsius to 2600 degrees Celsius. And we've got this information here. We have the specific heat of copper being 0.092 calories per gram degree C. What's different about this than what we had Tuesday when we were talking about water?
The specific heat of copper doesn't change in its different states.
Okay, so we're going to just use this 0.092 solid, liquid, and gas. So it'll make those 5 equations calculations turn into just 3 calculations. We've got a melting point, a boiling point, and a heat of fusion. So what's this heat of fusion for?
Isn't it the last?
Look at the value. Look at the 2 values for the heat of fusion and the heat of vaporization.
It's a Q value, correct?
It's an H value. What do we use this for? Let's skip it. What do we use this one for? The amount of energy needed to change to a gas. This one's a lot easier to see because it says vaporization. This one says fusion, so it's like I'm not 100% sure what that means, but what do we mean by that?
Oh,
Going from a solid to a liquid.
Yeah. So the heat of fusion is the amount of energy needed to go from a solid to a liquid. And it's actually, what's funny about this number compared to the number we had for water? Do you remember what it was?
About half.
Yeah, it's 60% of what that was. It's easier to liquefy copper once it gets up to its melting point than it is to liquefy water once it gets up to its melting point. Not the same with the vaporization, right? It's 2.5 times harder to vaporize it once I get to the vapor phase, which is why when you're doing any of this stuff, you always actually need to do experimentally to determine what these values are. It's not something you can be like, oh, this is copper, so the number's going to be something like this. For every one of these substances, somebody actually went and did an experiment like you guys did on Tuesday for this to figure out what these values are. Okay, so what we're looking at again is temp, time, this. So we've got a solid, we've got a liquid, we've got a gas, and this is melt, and this is boil or vaporize, whatever. And we need to figure out how much energy for each of these chunks. But since we've got a specific heat for all 3 phases that's the same, then this piece and this piece and this piece are all going to be handled by which equation? Q equals Cm delta T. How do you know you have to use this one?
Because it's on the increasing part of the graph.
What does that mean for this though? It is on the increasing.
It's heating up.
It's heating up. The temps change. This right here, the temperature's changing. It's not that it's gaining energy because it's gaining energy at all 3 of these spots. But this is these sections are the section where the temp's going up. So I can't use it there or there because there's no temp change. So I'm going to use 0.092 calories per gram degree C. And my mass is 250 grams. So we can cancel out the gram unit. And what's my change in temperature?
It's 2,578.
Just subtract off, right? So then I'll throw 2,578 degrees C here, cancel out the degrees C here, and I'm going to get a total heat 59,000 something. We only have 2 sig figs, so 59,000 will be fine. Calories. So it takes 59 calories to take this copper from basically room temperature up to 2,600 degrees, but that doesn't account for the fact that we need to boil it and melt it. So let's account for that. So to melt this, I'm going to take 49 calories for every gram of copper, and I've got 250 grams of copper. So that's going to give me a Q value, what is that? 49 times 250? 12,250 calories. So to 12,250 calories to melt this solid copper once I've gotten up to 1,085. And then if I'm going to boil it, once I've gotten up to this 2562, I'm going to need 1212 calories per gram, and again 250 grams. So 1212 times 250. So 303,000 calories. So 303,000 plus 59,000 plus 12,250. And I have, with 2 sig figs, I have 370,000 calories. That's adding this guy and this guy and this guy up, and then only 2 sig figs because we've got this 250 number, got the 22 number, got the 26 number, 2600 number. Okay, is that a lot of calories? Yeah, sorry, go ahead.
So the boiling, the fusion and the vaporization, those are the enthalpy values in your M8, they like the. Yeah.
Yep, those are the enthalpy values. So you're going to use this equation twice, once for when you're melting it, once for when you're boiling it, and those heats of fusion. So the way this would be written would be H fuse and then H vape, if you see it symbolized. It's probably easier to see it like that because then you know you're talking about enthalpy. Any more? Anything? Yeah.
So how come vaporization is just so much harder to do than?
We're going to talk about this. I can't remember if it's next set of notes or the set of, I think it's 2 sets of notes from now, maybe 3. When you're in the solid state, all the atoms or molecules are touching. When you're in the liquid state, they're still touching. But what happened during that melting process? We talked about on Tuesday. They're broken free of their position. So they can move around, but they're still in contact with each other. When I turn them into a gas, what do I have to do? I have to fully separate them all. So you picture a copper atom being attracted to another copper atom. When it's stuck in place and they just get to roll over the top of each other, it doesn't take a ton of energy to get them to be able to move. But then if I want that copper atom to fully be ejected from the rest of that, I got to put a lot more energy in it. Okay, this curve should be pretty easy, especially after what we just talked about. But, and you can answer these questions in this one very descriptively and very scientifically, or you could answer this using very small words that are very that are used a lot just in regular language. So tell me what's happening between U and B. Molecules, particles, atoms, particles are speeding up. That's it. Increase in speed of the substance. What's happening between W and X? Kaylee. Molecules are speeding up. Y and Z? Speeding up. Anytime I've got a temperature change, what's happening is the molecules are speeding up. So what does that mean for the flat portions? Bonds are being broken, and they're not speeding up. They're moving at the same speed. They're just disconnecting themselves from each other or fully letting go of each other. So between V and W, you can say bonds are being broken. And what's happening between X and Y? Bonds are being broken. So the flat sections, bonds are being broken. The angled sections, the particles are speeding up. Okay with that? If you think about it with just like water, take a pot of water and drop an ice cube in it and put it on the stove, and you turn the stove top on, and now the pot's getting hot and the ice cubes are getting hot. The ice cubes are, those water molecules are going to vibrate faster until they break free from each other. So they were moving faster and faster and faster, then they let go, and then you kept the heat on, so then the water temperature was going up and the molecules were moving faster and faster and faster around inside that pot. And then they went to their boiling phase where all the bonds were being broken, and I guess if you had a top on it, then they would move even faster if you kept them in a confined space in like a pressure cooker or something. Okay, that's it.